What if I told you that everything we need to become a spacefaring civilization is already within our reach, but the obstacles standing in our way might be far more formidable than you ever imagined? Look at this map of Earth, and then imagine spreading humanity across the solar system. The Moon, Mars, the moons of Jupiter. These aren't just distant dreams anymore. They're becoming engineering problems that we're actively trying to solve. But here's the thing. The challenges we face aren't just about building bigger rockets or designing better spacecraft. They run deeper than that. We're talking about the physics of human bodies in low gravity, the economics of launching billions of tons of material into space, the psychological toll of isolation millions of miles from home, and the sheer technical complexity of creating self-sustaining habitats on worlds that will actively try to kill us. This video is going to walk you through the greatest obstacles to space colonization, the real barriers that stand between us and becoming a multi-planetary species. And I want you to understand something crucial. Overcoming these obstacles isn't impossible. It's just going to require us to think bigger, work harder, and push the boundaries of what we believe is possible. So let's dive in. Let's start with the most obvious challenge, the sheer cost of space colonization. We're not talking about millions of dollars here. We're talking about hundreds of billions, potentially trillions of dollars, across the full timeline of establishing permanent human settlements beyond Earth. To put this in perspective, the entire Apollo program, which landed 12 people on the Moon between 1969 and 1972, cost approximately $280 billion in today's money. That was for a handful of brief visits. Now imagine the cost of establishing a permanent base with hundreds or thousands of people, complete with life support systems, habitats, resource extraction facilities, and the infrastructure needed to sustain human life indefinitely. The economics are staggering. Every kilogram of material we launch into space costs thousands of dollars. A single mission to Mars with a crew of 6 could cost anywhere from $500 billion to over $1 trillion when you factor in all the supporting infrastructure, training, equipment, and contingency planning. And that's just one mission. Real colonization means repeated missions, continuous resupply operations, and the development of entirely new industries in space. We need to make space cheaper. That's where reusable rockets come in. Companies like SpaceX have proven that we can land and reuse orbital-class rockets, which dramatically reduces launch costs. But we need to go further. We need to develop in-situ resource utilization, the ability to extract water, metals, and fuel from the Moon and Mars themselves. We need space elevators or other revolutionary transportation systems. We need to create an economy in space where the cost of operations comes down, not because of government subsidies, but because there's genuine economic activity happening up there. This is perhaps the biggest hurdle we face, because money drives everything. Without solving the economic problem, no amount of technical brilliance will get us to the stars. Now let's talk about the biological and physiological challenges, because this is where things get really complicated. The human body evolved on Earth under very specific conditions. 1 gravity, a magnetic field that protects us from radiation, an atmosphere that shields us and provides oxygen, and a temperature range that our biology can handle. The moment we leave Earth, we're asking our bodies to adapt to environments they were never designed for. Earth's magnetic field and atmosphere protect us from cosmic radiation and solar radiation that would otherwise bombard us with lethal doses. On the Moon, there's virtually no magnetic field and no atmosphere. On Mars, the magnetic field is essentially gone, and the atmosphere is so thin it provides almost no radiation protection. Astronauts on the International Space Station, which is still within Earth's magnetosphere, receive radiation doses roughly 150 to 200 times higher than people on Earth's surface. Now imagine being on Mars or the Moon for months or years. The accumulated radiation exposure increases the risk of cancer, cataracts, damage to the nervous system, and other serious health problems. We're developing shielding technologies, and we know that regolith, the rocky soil on the Moon and Mars, can provide radiation protection if we build habitats underground or cover them with layers of soil. But this adds complexity and cost to construction. Then there's the issue of gravity. The Moon has about 16% of Earth's gravity. Mars has about 38%. We don't actually know what the minimum gravity is for long-term human health. Studies on the International Space Station show that microgravity causes muscle atrophy, bone density loss, vision problems, and cardiovascular deconditioning. Astronauts can lose up to 20% of their muscle mass in just 5 to 11 days in space. Over months and years, this becomes catastrophic. We think that partial gravity might be better than zero gravity, but we're not certain. It's possible that 38% gravity on Mars is enough to maintain human health, but we won't know for sure until we get people there and study them over extended periods. And here's the thing, if it turns out that humans can't maintain their health in low gravity, we might need to create artificial gravity through rotation, spinning habitats to simulate Earth normal gravity. That's possible in theory, but it adds enormous complexity to habitat design and construction. There's also the psychological dimension of space colonization that we often underestimate. Imagine being one of the first colonists on Mars. You're 225 million kilometers from Earth. The round-trip communication delay is between 3 and 22 minutes, depending on orbital positions. You can't just call home and talk to someone in real time. You record a message, send it, and wait for a response. Your support network is limited to the few hundred people who are with you on Mars. If something goes wrong psychologically, if you experience depression, anxiety, or a psychological crisis, your options for treatment are severely limited. You can't be evacuated home in an emergency. You're committed to being there for at least 2 to 3 years until the next launch window opens. The isolation, the confinement, the distance from Earth, and the high-stakes nature of the mission create a psychological environment unlike anything humans had experienced before. We've studied isolation in Antarctica, in submarines, in the International Space Station, and in analog missions where crews live in Mars-like habitats on Earth. What we've learned is that isolation does affect people. Some adapt well, others struggle. There are personality conflicts that can escalate in confined environments. There's the phenomenon of the third quarter phenomenon, where morale and motivation dip significantly in the middle of a long mission. We need to select colonists carefully, provide them with excellent psychological support and training, design habitats that provide adequate privacy and psychological comfort, and maintain strong communication with Earth. But ultimately, we're asking people to do something that no human has ever done before, and we can't fully predict how they'll respond. I want to pause here and remind you of something important. Yes, these obstacles are real and significant. Yes, they're going to require innovation, investment, and determination to overcome. But here's what makes this so exciting. We're not speculating about whether these problems can be solved. We're actively solving them right now. SpaceX is developing the Starship, a fully reusable super heavy lift vehicle designed specifically for Mars colonization. NASA's Artemis program is returning humans to the moon and establishing a sustainable presence there. Private companies are developing life support systems, in-situ resource utilization technologies, and habitat designs. Scientists are studying the long-term effects of radiation and low gravity on human physiology. Psychologists are developing better selection criteria and support systems for isolated crews. The obstacles are real, but so is our capability to overcome them. If you're passionate about space exploration and the future of humanity, this is exactly the kind of challenge that should inspire you. The people working on these problems right now are the pioneers of a new era. And if you want to stay updated on the latest developments in space engineering and exploration, subscribe to Future Frontiers. We cover the innovations and breakthroughs that are making space colonization possible. Let's zoom out across the solar system for a moment and talk about the technical challenges of actually building and maintaining habitats on other worlds. Now let's consider Mars specifically, since it's the most likely target for human colonization in the near term. Mars is a hostile environment in almost every way. The average temperature is minus 63 degrees Celsius, with lows reaching minus 125 degrees Celsius at the poles during winter. The atmospheric pressure is less than 1% of Earth's, which means you can't go outside without a pressurized suit. The soil contains perchlorates, which are toxic compounds that can damage the nervous system and thyroid. The dust is incredibly fine and abrasive, and it can get into equipment and cause failures. There are dust storms that can last for months and cover the entire planet. The day is about 40 minutes longer than Earth's, which messes with circadian rhythms, and there's no liquid water on the surface that we can access easily. Though, there is water ice at the poles and possibly underground aquifers. Building a habitat on Mars means creating a pressurized structure that can withstand the extreme cold, the low pressure, the abrasive dust, and the thermal cycling between day and night. You need power generation systems, either nuclear reactors, solar panels, or some combination. You need life support systems that can recycle air and water with extremely high efficiency. You need to extract water from the ice or subsurface, process it, and use it for drinking, hygiene, and potentially producing fuel and oxygen. You need to grow food, either in pressurized greenhouses or through some form of hydroponics or aeroponics. You need to manage waste. You need to maintain equipment in an environment that's actively trying to break it. All of this has to be done with minimal resupply from Earth. The goal is to create a truly self-sustaining colony that can survive and thrive even if supply missions from Earth are delayed or interrupted. This is an engineering challenge of staggering complexity. We have theoretical solutions for most of these problems, but implementing them in the actual Martian environment is going to require testing, iteration, and refinement. The first colonies will likely be small, maybe a few dozen people, and heavily dependent on Earth for supplies and support. Over time, as we learn what works and what doesn't, we can expand and increase self-sufficiency. But it's going to be a gradual process. Consider the example of the Mars Science Laboratory, which landed on Mars in 2012. That single rover cost $2.5 billion to design, build, launch, and operate. It's one vehicle. Now think about the infrastructure needed to support human colonists. Habitats, laboratories, greenhouses, power plants, water extraction systems, medical facilities, and redundant life support. The complexity multiplies exponentially. We're not just sending a rover. We're sending an entire civilization's worth of equipment and supplies. Then there's the challenge of planetary protection and contamination. When we send spacecraft and humans to Mars, we inevitably bring Earth microbes with us. These microbes can survive the journey and potentially contaminate the Martian environment. Now, we don't know if there's life on Mars. We haven't found any evidence of it, but we haven't looked everywhere either. There could be microbial life in subsurface aquifers or protected environments. If we contaminate Mars with Earth life before we have a chance to search for native Martian life, we might destroy evidence of life that existed independently of Earth. That would be an enormous loss, scientifically. So we have protocols to sterilize spacecraft and equipment before launch, and we're careful about where we land and what we do on the surface. But it's impossible to completely eliminate all microbes. We can only reduce the risk. As colonization expands and more people are on Mars, maintaining planetary protection becomes increasingly difficult. Eventually, we might have to accept some level of contamination and focus instead on preserving areas of scientific interest. But this is a genuine ethical and scientific challenge that we need to think carefully about. The Moon is less of a concern because we haven't found any evidence of life there, but it's still worth being thoughtful about our impact on other worlds. We're not just engineers and explorers. We're also stewards of the solar system. Let's also talk about the challenge of establishing supply chains and trade networks in space. Right now, everything we do in space is incredibly expensive because we're launching from Earth's gravity well. Every kilogram costs thousands of dollars. But what if we could establish a lunar base that extracts water and oxygen from the regolith? What if we could mine asteroids for metals and minerals? What if we could manufacture components in space using 3D printing and other advanced manufacturing techniques? Suddenly, the economics change. Instead of launching everything from Earth, we could launch raw materials to an orbital manufacturing facility, process them there, and assemble spacecraft and habitats in space. This would be far cheaper than launching finished products from Earth. But it requires developing entirely new industries and supply chains. It requires investment and risk-taking. It requires companies and governments willing to bet billions of dollars on technologies that haven't been proven at scale yet. We're starting to see this happen. Companies like Axiom Space are building commercial space stations. Companies like Relativity Space are developing 3D printing for rockets. Companies like Planetary Resources were exploring asteroid mining, though the company was acquired by Arcade Astronautics. There's genuine momentum here, but we're still in the early stages. We need more investment, more innovation, and more companies willing to take risks. The good news is that the economics are starting to make sense. As launch costs come down, as reusable rockets become more common, and as demand for space-based services increases, we're going to see more private investment in space infrastructure, and that's going to accelerate the timeline for colonization. Consider the economic shift that happened in the terrestrial shipping industry. In the 1950s, the cost of shipping goods across the ocean was prohibitively expensive for most products. Then, containerization was invented. Suddenly, shipping costs dropped dramatically, and global trade exploded. We're potentially at a similar inflection point in space. Reusable rockets are our containerization. Once we solve that problem comprehensively, entire new industries become viable. Finally, let's talk about the regulatory and governance challenges. Right now, space is governed by the Outer Space Treaty of 1967, which says that no country can claim sovereignty over celestial bodies, but it also says that countries are responsible for the activities of their nationals in space. This creates an interesting legal situation. If a private company wants to extract resources from the moon or an asteroid, what laws apply? Who regulates them? Who do they pay? These are questions we're still working out. Different countries have different approaches. The United States has passed laws allowing private companies to own resources they extract from space. Luxembourg and other countries are developing their own space resource laws. But there's no global agreement yet on how this should work. As space colonization expands, we're going to need clearer international agreements about property rights, resource extraction, environmental protection, and dispute resolution. We might need to establish international bodies to govern space activities, similar to how we govern the oceans. This is a complex diplomatic and legal challenge that's going to require cooperation between nations. It's not as glamorous as engineering challenges, but it's just as important. We can't colonize space if we don't have clear rules about who can do what and how conflicts will be resolved. The good news is that there's genuine interest in solving these problems. International organizations are working on space governance. Countries are negotiating agreements. The space community is thinking about these issues, but we need to move faster. As commercial space activity accelerates, the legal framework needs to keep pace. So here's what I want you to take away from this. Space colonization faces real, significant obstacles. The costs are enormous. The biological challenges are serious. The technical problems are complex. The psychological demands are intense. The engineering requirements are staggering. The regulatory landscape is unclear. But none of these obstacles are insurmountable. Every single one of them is a problem that we're actively working on solving. Every single one of them is an opportunity for innovation and breakthrough. The people who solve these problems, the engineers, scientists, entrepreneurs, and explorers who figure out how to make space colonization work, they're going to be remembered as some of the most important people in human history. They're going to be the ones who took humanity to the next level. And if that inspires you, if that makes you want to be part of this effort in some way, then you're already thinking like a space colonist. The future isn't written yet. It's being built right now by people who believe that humanity's future extends beyond Earth. Subscribe to Future Frontiers for more on the engineering and innovation driving space exploration forward.